The year is 1974. How do you hit a moving target with a gun attached to a moving platform in unfavorable wind conditions? Well, first you would need some kind of accelerometer and a gyroscopic sensor capable of providing dual-axis stabilization so you can actually keep your gun on the target. No problem, we've had stabilized guns for years. Then you'll have to integrate a crosswind sensor and ambient temperature sensor so that it's possible to obtain atmospheric data. Oh, and you'll also need a laser so you can accurately gauge the distance of whatever you are engaging. Now that you have all this information, obtained by the aforementioned subsystems, you'll need to harmonize it into something that can be used to form a firing solution. This is an especially complex task. It would be rather difficult to do this manually on the modern battlefield, loaded with obscurants and missile systems. How can we ensure that the operator of this gun is capable of focusing on everything going on in front of him, so he doesn't have to worry about all of this data? Well, it is the 1970s. The aviation industry is abuzz with talk of automation relieving the individual of these exact burdens. And the Army has caught on as well, that in a few years divisions will receive a command and control system akin to those used by the PVO. That's it. You need a computer.
Она не актриса, не кинозвезда, она не любовница и не жена. Она теряет рассудок при слове кровать. Она знает, как лечь, но не знает, как встать. И недоступна при свете кокетка в ночи. Ее любимая фраза: лег и молчи. Она помнит запах настоящих мужчин. Она знает средства от ранних морщин. А ну давай, слабый пол, танцуй постельный рок-н-ролл. Это шанс, а не прикол, когда танцует слабый пол рок-н-ролл. А ну давай, слабый пол, танцуй постельный рок-н-ролл. Это шанс, а не прикол, когда танцует слабый пол рок-н-ролл. Она не похожа на наших подруг. Она положит любого под высокий каблук. Перед ее красотой бледнеют зеркала. Она немногое даст, зато возьмет сполна. Она сильна и строптива, как ночью гроза. И смотрит как-то игриво, не мозоля глаза. Она не принимает пива, не курит пегас. И знает цену за каждую ночь и за час. Ну давай, слабый пол, танцуй постельный рок-н-ролл. Это шанс, а не прикол, когда танцует слабый пол рок-н-ролл. А ну давай, слабый пол, танцуй постельный рок-н-ролл. Это шанс, а не прикол, когда танцует слабый пол рок-н-ролл. Она любит песни группы Кармен. Она любит вольный вечер и ненавидит плен. Ей нельзя быть одной, она не может грустить. Она довольна собой, и я хочу ее любить. И я хочу к ней прижаться небритой щекой. Да прекрати ты ломаться, я совсем неплохой. Пусть и я не вышел рылом, карман мой пустой. Зато как в песне поется, прекрасен душой. А ну давай, слабый пол, танцуй постельный рок-н-ролл. Это шанс, а не прикол.
Following the Second World War, across the world, tank designers were scrambling to integrate lessons imparted by their experiences with the conflict. In the Soviet Union, this manifested in the desire to improve the ability for tanks to fire accurately on the move, the introduction of larger guns to extend the range in which targets could be engaged, and reductions to the speed in which the former could be conducted. This prompted the development of dependent and independent sight stabilization. T-54 would be the first tank in the USSR to employ dependent stabilization. This meant that the new TSH-2 sight was linked to the stabilization of the gun. This presented some issues at higher speeds and during loading, resulting in the development of sub-stabilization. This allowed the sight to switch to a vertical stabilization mode to compensate for the previously described conditions, when the gun would lock or engage its hydraulic stop. While this was functional for a time, it was evident this was not the way forward. To correct for errors generated by this layout and improve accuracy, Independent stabilization for both the sight and the gun was needed. This concept was first tested on TPS-2, used by T-10A. To achieve this effect, 2 gyroscopes were introduced into the sight, one for stabilization and the other for the generation of lead angles, or in layman's terms, the angle through which the gun must be traversed from the line of sight to compensate for its own motion and the target's. The sight also included what was known at that time as a firing automaton, which ensured that the gun was fired the moment the highest likelihood of striking the target was reached. Interestingly, according to some sources, this optic used a domestically produced variant of a German gyroscope employed in the V-2 rocket. Following the introduction of TPS-1, T2S would surpass its capabilities by ushering in an innovative delta-D system, which automatically measured the speed of the vehicle via a tachometer, allowing for the distance it traveled relative to the target to be deduced and subtracted from its range. It would also take into account the orientation of the turret in azimuth and generate new calculations using a cosine function. This meant that the gunner only had to take a single range measurement, after which he was free to engage the target and the driver was free to maneuver the vehicle. At this point, the primary limiting factor was no longer the ability to keep the gun on the target, but range finding to facilitate an accurate shot. In the late 1950s, KMZ had proposed a myriad of options for next-generation sights, but they all proved uniquely problematic and were not adopted. There were also frequent disagreements between those who believed their solution was best. A conclusion on stereoscopic versus coincidence was going nowhere. A radar rangefinder was considered at this time and was tested on T-10, but did not see continued investment. Those who recall the issues plaguing fighter-bomber development discussed in earlier videos have likely noticed by now that the exact same disagreements and solutions are repeating themselves with startling consistency. This problem persisted at the highest levels. The main artillery directorate preferred non-adjustable stereoscopic sights, while the main armored directorate were in favor of coincidence rangefinders. A solution was needed, as at this time both the T-62 and T-55 were equipped with a biological fire control system, known as the gunner, who was responsible for range finding, compensating for any atmospheric conditions, and tracking the target while in motion. To settle the dispute, KMZ developed a sight combining both range-finding principles. This concept was called the TPD, or Tank Sight Rangefinder. The first TPD to enter service would do so alongside T-64, under the designation TPD-43B. Production would start 2 years prior in 1964. T-64A OBR 1972 would make use of a variant of the 43B, designated TPD-2-49. This optic still required a degree of skill to use effectively, as the gunner had to concentrate on the target and align the images provided by the two lenses. One of the more important introductions present within TPD-2-49 equipped tanks was an early ballistic computer, very similar to that of the M13 in service with M60. Calling these systems computers is somewhat generous, but they were exceedingly innovative as far as the US and Soviet Union were concerned. Their purpose was to correct the range estimation to be coherent with the loaded ammunition type. In both computers, this was achieved through a set of cams, each corresponding to a different type of projectile, which adjusted the sight accordingly. Because M60 is manually loaded, the computer must be informed of a change in ammunition type by the crew. T-64 streamlines this process through its autoloader, which tells the computer the ammunition it is loading, depending on what has been selected, allowing for automatic correction. By the end of the 1960s, the Ministry of Defense began to obsess over lasers. It only made sense that this technology would be applied to armored vehicles, considering that laser rangefinders were already in use and providing information to MiG-23B's analog computer. Before lasers could become a reality, radar rangefinding was considered yet again between 1964 to 1966, in conjunction with the experimental 1G12 sight. Despite the application of new technologies, like photoelectric sensors to detect if firing conditions had been met, the system was incapable of achieving a considerable increase in accuracy over conventional solutions. One year later, it was finally time for an experimental laser rangefinder to begin development. TSNIIAG, who was tasked with its creation, used the then obsolete T2S site stabilization system as a foundation to ease development, and combined it with a laser rangefinder designated 1D7, which required a lot of troubleshooting before it would mate with the optic. This system, now known as 1K3, almost immediately began testing on a T64 in early 1967. 1K3 would soon evolve into 1G20, which employed photoelectric sensors likely similar to those used in 1G12, and a new 1D10 laser rangefinder, developed by NPZ, which proved far more reliable when compared to 1D7. 1D10 used a very strange system to create a single ranging pulse. What is described as a liquid shutter was present. This was a barrier that filled with liquid to shunt further irradiation once necessary data had been obtained. To add to the existing complexity of this system, the transmitter was filled with an alcohol-based coolant. Eventually, it became possible to eliminate this measure and simplify the design. While laser rangefinders were in development, a relatively unique proposal was being considered to extend the range at which enemy armored vehicles and infantry could be reliably defeated. The gun-launched anti-tank missile. It should be noted that initially this concept was considered a guided projectile and only later became a missile, but I will be referencing it as such from now on, as it is easier than saying a guided projectile over and over again. Previously, this had been a subject of great interest dating back to the 1950s, but every attempt had failed miserably for one reason or another. Now, with the push for larger caliber guns to be integrated on the next generation of main battle tanks, like the T-64, it made sense to give this concept one more try. This missile would have to be developed from scratch, as those used by Object 775, despite being 125mm, were not suitable, as they were designed for use with a rifled gun. Additionally, the guidance equipment required to employ this weapon was large and impossible to seamlessly integrate into T-64. After this idea fell through, the application of 9M14 was briefly considered, as it too had a caliber of 125mm. But this similarly did not go anywhere, as the missile would have been impossibly difficult to keep on target while the tank maneuvered. As a result, on December 28, 1966, OKB-16, after a brief reorganization period, would begin work from the ground up on a new 125mm guided munition, which would receive the designation. When work began on Cobra, one of the 3 ammunition types employed by the prospective T-64A had to be selected as a foundation. 3OF-19 was chosen for its propellant charge, as it offered a nominally lower muzzle velocity of 850 meters per second. It was expected that the missile would feature a guidance system almost identical to Draken, used by IT-1, even employing its sighting system. OKB-16 had gained a lot of experience working with radio-controlled missiles over the years, and so it seemed reasonable to move forward with this technology. Additionally, there were some unique advantages presented by this solution, all of which had been demonstrated by Corral, Falanga, and Draken. Wire links are affected by terrain and electrical obstacles, and could impose limitations when launched over water. These were not concerns for the aforementioned missile systems. Wire breakage and issues surrounding spooling speed would also be ablated, meaning the missile could be fired on the move at greater velocities. However, radio links are not a perfect solution, as they can theoretically be jammed in a far simpler fashion when compared to wire-guided missiles. But this was easier said than done, as first the launch would have to be detected, after which the missile would need to be tracked as it approached the target, and the receiver sufficiently suppressed. This was, in many regards, an impossibility at the time, especially when one considers that the ideal maximum engagement range for Cobra was around 4,000 meters, which, according to program requirements, it should have been able to reach in roughly 6 to 7 seconds. As a result, it is exceedingly unlikely that anyone being targeted by this munition would be aware of the fact that they had been engaged until it was already too late to do anything about it. By 1967, a preliminary design would be completed, and ballistic tests conducted, with experimental projectiles, mainly to confirm the functionality of its gyroscope. 2 launches transpired, while the tank firing the missile was hit with an artillery barrage to confirm that it could be used in extreme conditions. TPD-2-49 and 1K3, which, as discussed earlier, was undergoing tests at this time, were integrated with the missile, but the former was soon dropped as laser rangefinders were slated to replace conventional rangefinding solutions. It was also understood that 1K3 was too complex to manufacture at scale, and very clearly not the way forward. TSNIIAG was tasked with creating a next-generation fire control system that would ideally take its place at some point in the future, but no deadline had been established. When tested with the aforementioned sighting systems, some problems were revealed that instantly caused the program to stall. The cannon, while impressive, kicked up a screen of debris that made it impossible to guide the missile for a short period. To solve this problem, a muzzle device was introduced, which worked wonderfully, but had the unintended side effect of removing the gun's ability to fire conventional APF-STS, as the fins refused to deploy properly. This failure nearly killed the program, but the quick thinking of the team working on the system resulted in its continued development. They proposed soft-launching Cobra instead. To accomplish this, first the propellant charge was reduced significantly, and a solid-fuel rocket engine was introduced. This slowed the missile down somewhat, but this was not terribly problematic, as the introduction of deployable wings improved stability. This was done with a pyrotechnic charge. Due to the autoloader's application of 2-piece ammunition, a coupling mechanism had to be designed, so that the engine and the rest of the missile could be bound in the breech. This meant that the only way to unload Cobra after it had been coupled was firing the gun, a necessary compromise. Initially, the autoloader's rammer did not possess enough energy to engage the mechanism, and so a new rammer was developed, which received the designation 6ETS-40. In 1968, this new layout was approved, and 165 were fired to confirm its functionality. But OKB-16 was not out of the woods just yet, as alongside these accomplishments, Kolomna began to see progress on a competing design they had been working on, known as Gurza. It differed mainly in the application of an infrared command link, which actually ended up biting the team behind the system, as this complex was continually delayed. In 1971, it would be cancelled, as Cobra had progressed to its final stage of testing, following the installation of a complete prototype set, including guidance on a T-64 in 1969. This resulted in the Izhevsk mechanical plant preparing to manufacture the system. To allow 1G20, which was discussed earlier, to track the position of the missile, a device was installed in the sight which would register the light of a xenon lamp affixed to the rear of Cobra. This experimental system was designated 1OP73. Range-finding errors persisted, but 21 launches were conducted nonetheless. Unfortunately, the majority proved unsuccessful, primarily due to the especially poor quality of the 6B145 battery and DKSM 600 xenon lamp installed within the missile. Despite the state of Cobra's subsystems, Gorokovets was selected as the range in which the system would undergo state tests. This is where Falunga and Schmel were tested, so it was on brand. 3 T-64A tanks were modified for the upcoming trials. The first would arrive at the range on February 23rd of 1971. The problematic components were indeed problematic. Only half of the launches were successful. As these tests took place, OKB-16 was hard at work modifying DKSM-600. This was done an unspecified number of times. Each iteration would be tested by a machine that simulated launch conditions to confirm if the changes had been successful. This actually ended up working, but only alongside changes to the missile's engine, which turned out to be generating so much smoke that it interfered with the feedback channel. Additionally, one OP-73 suffered unsatisfactory vibrations when the tank exceeded 15 km per hour. Trials were halted, and OKB-16 got back to work refining the complex. In January of 1972, testing finally began to show some promise. A target at a distance of 4 km, moving at a speed of 35 km per hour, was hit, while the launch platform was traveling at 15 km per hour. A huge success. Remember that fire control system I mentioned earlier? The one that was under development in pursuit of replacing 1K3? Well, at this time, the program had been shuffled around somewhat. The TSKB of KMZ was slated to take over the project, which was now designated OB, or 1A33, after the major river in western Siberia, as TS and IIAG had been reassigned to the development of fire control for missile systems. This was a rather interesting decision as KMZ only had experience in the production of sights, not fire control systems. It is for this reason that KMDB and Leningrad had to work directly with KMZ to realize the complex. In 1973, 1A33 would become a part of the T-64A-2M program. OB would be rather ambitious. It was to integrate a myriad of emerging technologies with the intention of creating a truly modern fire control system, such as a vastly improved laser rangefinder, sight, crosswind sensor, roll sensor, and most importantly, a proper ballistic computer to harmonize the information provided by these subsystems. Initially, it was not possible to develop a computer for the new fire control system. No organization existed that was free to work on it, or had the expertise to do so. It is for this reason that Professor Prasnukin at the National Research University of Electronic Technology, or MIET, spearheaded the concept. This would lead to the creation of 1V517, a strange analog ballistic computer with digital peripherals, which I will discuss in greater detail shortly. By May of 1972, 2 tanks operating an experimental version of 1A33 were undergoing tests at Gorokovets. 350 rounds of conventional ammunition were expended at this time, which somewhat delayed Cobra launches. As a result, it was decided by both OKB-16 and KMZ that 3 more modified tanks were needed. These early models still used 1G21, as the site expected to replace them had not yet been completed. According to some sources, on August 17, 1973, T-80 was actually the first tank to see the unification of 1A33 and Cobra, but this flies in the face of every other account on the matter, so I will not be using that version of the story. When testing 1A33, the actions carried out throughout an engagement were broken into phases so that they could be measured independently. Phase 1, target search and detection, Phase 2, preparation for firing, and Phase 3, accuracy of the first round alongside subsequent shots. 1A33 was tested against T-62 and T-64A. A report was drafted, which I will read from now. During the experiments, the entire Stage 2 of the firing process was carried out both from tanks moving at speeds of 20 to 25 km per hour and from stationary tanks, firing at stationary targets. Gun loading during shot preparation was performed using mock rounds. The determination of temporal parameters for the shot preparation process was conducted during the engagement of both single targets and targets encountered during a breakthrough of the enemy's defenses. The disposition and nature of the enemy's actions corresponded to the organization and defensive tactics of NATO army units. Targets were positioned taking into account terrain features, and were camouflaged to create detection parameters for the crews that were close to real ones. The total number of simulated and real targets was approximately 50. During the trials, the positions of the targets were varied laterally and in depth within 50 to 100 meters. T-55, BTR-152, grenade launchers, tanks in entrenchment, ATGMs, and machine guns were used as targets. During the research, the time required to perform individual operations and the entire process was recorded using K12-22 multi-channel oscillographs. Electrical signals taken from the operating elements of the control system were used for recording. Voice information was recorded using tape recorders connected to the tank intercom system of the vehicle under study. T-62 took approximately 38 seconds to prepare a shot while stationary, and 57 while moving. T-64A took 30 seconds while stationary, and 37 seconds while moving. 1A-33 took just 18 seconds while stationary and 25 seconds while in motion. Analysis of the shot preparation cycle diagrams for the investigated fire control complexes shows that turret slewing during target designation and the exchange of information during task assignment occur in parallel and do not exceed 4 seconds. Target detection for the gunner, after target designation, begins before the tank commander has finished assigning the combat task and takes 4 seconds from a stationary position and 8 seconds when on the move. The largest share of the total shot preparation time on tanks, with manual preparation of firing data, and partially automated preparation, is occupied by the operation of range determination. Automatic range measurement using a laser rangefinder has significant advantages over the above methods, and is practically determined by the time required to place the sight mark on the target. Full automation of the generation and input of firing data reduces shot preparation time compared to partially automated fire control systems by 12 seconds, and compared to non-automated fire control systems by 20 to 32 seconds. In July of 1973, 3 years late according to the official deadline, 44 Cobra missiles were expended at the range. At this point, it should not be a surprise to anyone that after 12 launches only 3 hit their targets. With each miss, a new component failed. First, the gun would not fire due to an electrical issue. Next, the sun blinded the optical system, causing the missile to fly largely uncontrolled towards the target, missing it. Third time's the charm, well, maybe not at Gorokovets, as the guidance system failed entirely and the missile once again flew uncontrolled towards the target, and on the 4th launch of that day, the wing separated from the body of the missile mid-flight, causing it to careen into the ground. After the missiles were inspected, it was revealed that they had been produced to unsatisfactory standards, with many rough edges and faulty components. This time, OKB-16 added a diaphragm to the optical system, and a complex was introduced which would allow for the missile to remain stable even if the control signal was momentarily lost. Time to test the missile again! 6 wing breakages, 4 lamp failures, and 1 guidance failure later, and it was back to the drawing board. Additionally, 1G21 was once again hardened against harmonic disturbances. The test tanks were rebarreled as they had suffered expansion, and the lamps and batteries, still unreliable, were reconfigured. Finally, after a long break to work out a few more kinks, by the end of 1974, 19 missiles had hit their targets, and only 5 failures were recorded. However, a new issue was revealed when the breach was opened after firing Cobra, as the fighting compartment was filled with smoke. That same year, on the 1A33 front, 1G42 began development to replace 1G21. It would feature both vertical and horizontal stabilization. To modernize the laser rangefinder, a time-of-flight measurement device, known as IVI-1M, was developed using integrated microcircuits. In early 1975, a number of launches would occur, most of which were successful. However, the problem of dust being kicked up by the missile throwing off the site returned with a vengeance. This time it was a result of Cobra's engine, which threw obscurance into the air as it flew towards the target. This resulted in a new guidance mode being introduced, in which Cobra would climb to around 3 to 5 meters in altitude, before descending back into its standard flight profile 600 to 800 meters from the target. Despite the program's completion, it would not immediately see service on T-64 for reasons that I will go into shortly. At this time, T-80, T-72, and T-64 were still in competition with one another, to determine which would become the future of Soviet tank development. The installation of 1A33 and Cobra on T-64 gave it a serious lead over competing designs like T-80 and T-72. According to some sources, LKZ, who was developing the T-80, was actively lobbying to remove Kharkiv from power, and establish themselves as the leading design bureau. Morozov supposedly made this difficult, but in October of that year he would begin to put his retirement into motion. To make matters worse for Kharkiv, Ustinov, who was heavily in favor of the T-80, became Minister of Defense the following year. In 1975, while testing 2 T-64s equipped with 1A33 at a range in Smolino, a message was received that they had to remove one of the 1A33 equipped turrets and place it on a T-80. Apparently the gun present on the turret still attached to the T-64 was thermally unstable, and so T-80 outshot T-64 that day with an identical fire control system. Popov supposedly used this as proof that his tank was superior, but the record is somewhat hazy and this claim isn't actually supported in the wider historical record. Also in 1975, a meeting between Morozov and Prasnukin of MIET was organized but frequently delayed and postponed. It would not be until 1976 that Prasnukin would arrive with his team of specialists to speak with Morozov directly about improving the OKB's autoloader via the introduction of a new sensor system. They would also propose a myriad of fire control solutions, including a digital computer, which could be implemented in the future. After a period of debugging, dedicated to addressing the temperature sensor's refusal to allow 1A33 to fire the gun below -50°C, the complex was adopted alongside Cobra, entering service on T-64B in 1976, vastly improving its capabilities. In 1977, a gas deflector entered serial production to prevent Cobra from introducing fumes into the fighting compartment. In 1978, T-80B would be accepted into service, which introduced a number of improvements, including 1A33. While the system had technically been adopted, the road forward was not without its challenges. 1A33 was dizzyingly expensive, increasing the cost of the tank by a factor of 40% compared to T-64A. It was determined that the removal of Cobra would reduce this price by 18%, and so T-64B entered service without its missile, receiving the designation B1. Interestingly, despite testing the complex, T-80 would not enter service with 1A33. Plans were almost immediately made to produce a variant operating the system, which I discussed earlier. In 1977, Cobra would be fitted to T-80 as a part of the improvement program, which was largely an uneventful process. There has been a confusing amount of inconsistency regarding 1V517, the computer present within 1A33. It is believed to be digital by some, and analog by others. Yuri Apuktin, who was working at Kharkiv when the system was adopted, and supposedly had close contact with Prasnukin, meeting with him on multiple occasions, is under the impression that the computer is digital. Even being presented at the EVM-83 exhibition, which was partially dedicated to the display of emerging digital computers. In a more recent article that he authored for Top War, he continues to describe the machine as a digital computer. While a component-level diagram of 1V517 has not surfaced, this does not prevent one from inspecting the manuals dedicated to T-80 and T-64B, which feature a myriad of statements describing 1V517 that are uncharacteristic of digital machines. The most convincing of which include the presence of cosine potentiometer windings, mismatched signals, which are an analog feedback mechanism, the application of 400 Hz circuitry, which is a standard for electromechanical systems, and the fact that it is running on AC, which is uncommon for digital computers. Of course, this does not mean that 1A33 is entirely analog. In fact, most of the information that is provided to 1V517 is from digital systems, like the rangefinder. The complete 1A33 system includes 1G42, which, as discussed earlier, is the new laser rangefinder, 1B11 crosswind sensor, which functions only when a round is being loaded, 1B14 roll sensor, 2E26M hydraulic stabilizer, and the 1G43 shot resolution device, all of which communicate with one another to create a fully automated fire control system. 1G43 functions in a similar fashion to the shot automaton discussed earlier. It exists to close the gun's firing circuits when the mismatch between the actual position of the gun and where it needs to be are equal, taking into account the angular velocity of the target and lateral lead. It also generates the 27.8 to 31.2 volt 400 Hz reference voltage used by the computer. Because 1G42 resolves target range digitally, it is provided to 1V517 in an analog fashion, in the form of a voltage representing how long it took for the photodiode to be hit with a reflection. It is then adjusted based on what the computer has been told by the tachometer, crosswind sensor, roll sensor, selected ammunition type, and manual input data, such as the condition of the gun, ambient temperature, atmospheric pressure, etc. Once the range data has been modified, it is delivered to 1G43, which ensures that the gun has been updated to be congruent with the computed adjustment. Additionally, 1V517 is capable of automatically tracking a target by taking control of the turret after the gunner has completed a period of manual tracking. This is then adjusted according to the ammunition type to ensure that the target is hit. This isn't automatic tracking in the modern sense, which did not exist at the time. It is more so just a continuation of the gunner's actions through the computer. If the target changes direction, for example, 1V517 is not capable of accounting for this and would need to be adjusted again. To sum up everything I just said, the fire control system does not see the raw data produced by its various subsystems, including information about the target's range. It only sees the modified data provided by the computer, after all corrections have been issued and misalignments resolved. 1V517 talks to 2E26M through the difference in the gun's current position and the desired position. This comes in the form of a signal received by magnets that control pressure differentials. This causes the turret to rotate towards the reduction of the mismatch angle supplied by the computer. When launching Cobra, the light from its xenon lamp is received by a photodetector, which generates control voltages proportional to the deviation of the missile relative to the optic. These signals are used to generate commands, after which they are sent to an encoder, which reproduces them as coded bursts matching the corrections. These are then relayed over the radio command line to the missile, which reconverts them to voltages delivered to the gyroscope to adjust its flight profile. To increase the accuracy of the missile, additional commands including compensation for the missile's weight are delivered. The information transmitted to Cobra includes a series of unique letter codes to ensure that it is not identical to a similar command line that is being radiated nearby. This allowed for up to 10 Cobras to be launched in close proximity to one another. It was even possible to guide 2 of them towards a single target. This code was produced when the ammunition was indexed, and was determined by the designation given to the control complex, known as 9S461. In 1977, 12 missiles designated 9M112M and 2 missiles designated 9M112M2 were produced. These were prospective variants of Cobra, promising a 20% and 40% increase in penetration respectively. In 1979, the former would enter service. That same year, tests were carried out at Gorokovets to determine the efficacy of employing Cobra against helicopters. Here it was determined that it was indeed possible to engage helicopters at ranges of 4 kilometers, flying at speeds of 300 kilometers per hour, at an altitude of 500 meters. In this case, the missile would not be lofted, instead it would fly straight towards the aircraft, as the risk of kicking up obscurance was ablated by the engagement parameters. This meant that alongside their anti-aircraft machine guns, tanks equipped with Cobra could defend themselves against helicopters. Even if they did not hit the aircraft, it would force the enemy to maneuver and possibly break off from the attack entirely. In 1982, it was finally time to begin introducing T-64B and T-80B into the GSFG. There were many factors influencing this decision, one of which was most certainly the fact that the moment anything appeared in Germany, it was immediately being observed by Western analysts. And indeed it would not be before long that a liaison would jump inside of an unattended T-64B and photograph 1G-42. This was described as the holy grail of the United States military liaison mission, and was actively being pursued even before these vehicles had been delivered. When deliveries began, they were piecemeal, 1 company per battalion. This would free up small batches of T-64A, which would be used to replace the T-62 still present in some formations, and any additional tanks would make their way to training units. In early 1983, the first T-80Bs would arrive, entering service within the 9th Guards Tank Division and the 27th Guards Motor Rifle Division. That same year, 7th Guards Tank Division and 10th Guards Tank Division received their T-64Bs. In 1984, this process would continue in other formations, and the 1 company per battalion rule would be followed throughout the 3rd Army and 20th Guards Army. By 1985, 2nd Guards Tank Army, 3rd Army, and 20th Guards Army were 1/3 T-64B equipped. Originally, it was believed that the T-80 would be more exclusive, only seeing deployment within the 1st Guards Tank Army, and 8th Guards Tank Army. This would change in 1984, when the decision was made to gradually equip the entire GSFG with T-80B. As these events transpired, there was much talk of the future of Soviet fire control development. Particular interest was placed on the introduction of digital computers. A publication discussing trends in the development of fire control reads as follows. In modern tanks, a human operator participates in solving the listed fire control tasks. The least automated process is the search for and detection of a target, using optical instruments. In real combat conditions, target visibility is difficult due to smoke and dust on the battlefield, as well as the enemy's use of camouflage, and the screening properties of terrain, natural and artificial cover. Experimental research shows that the target detection range under real tank operating conditions is comparable to the effective firing range, which imposes increased risks on the speed of modern fire control. In such conditions, the human operator experiences a severe limitation in time, which can lead to errors in weapon control and reduce firing effectiveness. The use of thermal imaging and radar devices in tank fire control makes it possible to increase target detection effectiveness under interference conditions, especially when this process is automated. One possible direction for solving this problem is the creation of an automated target reconnaissance system based on revealing demasking factors, whose sources are various types of emissions, laser, infrared, radar, as well as the enemy's activity. These automated target reconnaissance systems, or ATR, would significantly simplify target search, reduce the cycle time for determining target coordinates, and automate the target designation process. Further improvement in target detection effectiveness can be achieved within tank units equipped with special reconnaissance means based on the integrated analysis of various target signatures, with automatic transmission of target designations to individual tanks. A significant role in modern fire control is assigned to the human operator involved in the task. These shortcomings significantly affect the total error of the fire control system and reduce the effectiveness of the modern tank weapon systems. One direction for improving the accuracy and time characteristics of tank fire control systems is the use of semi-automatic tracking systems, or STS, with discrete control. STS would allow reconstruction of the target motion through a series of successive coincidences of the reticle with the target and automate the tracking process, leaving the operator only monitoring the function. Higher noise immunity, lower sensitivity to the control loop, and independence of the control signal law from the operator actions during coincidence intervals provide these systems with significant advantages compared to manual tracking systems. However, the accuracy of target motion reconstruction in STS largely depends on the accuracy of reticle-to-target coincidence, depending on many subjective human factors. The complete elimination of these factors is possible only through the use of automatic tracking systems, or ATS. Several approaches to building ATS are known, based on radar, laser rangefinding, thermal imaging, and spatial image filtering. None of these principles alone can ensure sufficiently high tracking reliability under combat conditions. Therefore, it is necessary to use integrated methods that exploit different target features, which mutually complement each other, combining thermal and radar means with optical, television, and electro-optical systems. This ensures tracking across a wide range of tactical and weather conditions. Anyone who is familiar with the Object 477 and Object 490 programs will notice that a lot of these factors are taken into account on these vehicles. Modern tank fire control systems have achieved a fairly high level of automation in gun laying to the predicted point. However, certain factors such as propellant temperature and barrel wear, caused by non-uniform temperature distribution in the ammunition stowage, partial replenishment of the ammunition load, and a wide variety of similar ammunition types with noticeable ballistic differences, require the creation of a special system for automatic input of this information into the fire control system during loading, together with the other input sensors used for solving the engagement problem. This should form the basis of the tank fire control system information measuring complex. Analysis of firing accuracy of modern tank weapon systems shows a reliable target hit probability of at least 0.9. This can only be achieved after firing several rounds. To reduce the time required to complete a combat mission, an automatic system for controlling and correcting firing results is required. It is crucial to accurately determine the lead movement. It is not possible to use a ballistic computer of the analog variety for this purpose, since the projectile time of flight is not computed with sufficient accuracy. Simultaneous tracking of both the target and the projectile allows sufficiently accurate determination of the lead moment, and therefore measurement of the total firing error, and computation of required corrections. Thus, a new approach to designing tank fire control systems is required, taking into account a wide range of tasks: the speed of their firing solution, the need for different channels of target information acquisition, the volume of information, and its rational use depending on tactical and meteorological conditions, and multi-mode operation of the fire control system. In other words, it is appropriate to consider the fire control system as an information control system, using an onboard digital computer. In this case, high reliability of instruments and stability of the fire control system during long-term tank operation is ensured by redundancy systems, self-adjustment, built-in automated testing, and diagnostic tools. Important directions in the development of new fire control systems include reducing cost, which I don't know how they would possibly achieve with all of the previously discussed concepts, decreasing overall dimensions, and increasing reliability, which also you will not be able to do if you are adding all of the above concepts, through the wide use of advances in electronics and the application of modular design principles. This paper is very interesting because it is relatively modern as far as its date of production was concerned, but manages to get a ton of things wrong, and this isn't terribly shocking. A few years before this, a relatively comprehensive Polish article was authored on the future of tank design in general, which discussed a lot of ideas like fuel cells becoming a standard, and every tank having an automatic cannon, 20mm or greater in caliber. It seems that in this case, the capabilities of the digital computer are being overestimated. These concepts would be pursued, however, in 1A42, a new fire control system being developed to replace 1A33. One of the core components of this complex would be 1V528, a further development of 1V517. It would be the first digital computer produced by MIET. When 1A42 was being integrated into 1A45, early examples employed 1V517 in place of 1V528, due to production issues, which were eventually resolved. It is described by the Bulletin of Armored Vehicle Technology as follows. At long range, 2 to 3 kilometers, errors have a significant influence on firing accuracy. To reduce them, it is necessary to develop more accurate algorithms and more advanced computers based on microprocessor technology. 1V528 indicates the possibility of solving this task. Accounting for numerous factors influencing firing accuracy can be carried out using a complex information-based measuring system. Work currently underway on the creation of laser locators forms the basis for creating a remote measuring device of atmospheric parameters. At large target range, the range of gun laying speeds increases, along with a high level of mechanical impacts on the gunner during tank movement, as well as the expansion of the range of firing tasks. Results of experimental studies of the STS as part of a tank show that their introduction into the FCX structure makes it possible to increase aiming accuracy of moving targets by 1.5 to 2 times. But since the participation of the human operator in the control process remains, it is not possible to achieve high firing accuracy. Maximum exclusion of the human from the gun-laying process is provided by the automated tracking system. Experimental studies show that the reliable target tracking using such an ATS is possible when using broadband optoelectronic systems. However, we would need a speed of 1 million operations per second to complete this task. Full-scale studies of ATS will make it possible to select the most optimal variants for the tank and determine ways of its improvement. I find the number 1 million operations per second to be especially amusing, considering that even massive Orbita computers present in Soviet aircraft at this time did not push anywhere near this compute speed. There are a few sources which claim that 1V528 was a hybrid computer, which is very likely, and would explain the presence of a similar control scheme to 1V517. Supposedly it was proposed as early as 1976, which would further verify its hybrid nature. 1A45 would first see use on T-80U and UD, featuring the new 1G46 sight, which came with a liquid-cooled laser encoding and transmitting unit, and integration with the vastly improved reflex missile in place of Cobra. But before 1A45 had entered service, another fire control system had been developed alongside it, which actualized 90% of the requirements discussed in the reports I just read from. It was an entirely digital system. All of the data it worked with was part of a wider architecture, which was itself digital. Even the manual entry of data, in case the fire control system failed, was done through a digital keyboard. The ballistic computer, managing the complex, was built on a domestic variant of the 8080 8-bit processor, allowing for a ballistic solution computation time of just 0.2 seconds. The computer was aided by an advanced laser rangefinder capable of accounting for multiple return signals, partial obstructions, and ambiguous reflections. This complex was unquestionably the most advanced fire control system produced within the Warsaw Pact. even integrating a laser warning receiver, allowing the gun to automatically salute towards a threat and the immediate discharge of smoke grenades to protect the vehicle. This was the future E.K. Potemkin so accurately described just 2 years prior in his publication Fundamentals of Tank Armament Design that I read from earlier. This incredible new technology would carry the Soviet Union forward into the unknown that was the next 2 decades of armored warfare. With the power of the microprocessor finally at the fingertips of the Soviet tanker, anything was possible. Wait, one moment, my apologies. I'm getting a call. Yeah. I see. It's Polish?